Okay, so page 7, if I remember correctly, we had gotten through these couple of free body diagrams here. The one diagram of when it is being allowed to just drop, and then another diagram of the forces when it hits the haystack. And I said, use that to help you answer the questions. Okay, so in question 1, oh, we already did question 1, right? We said that it was graph B because in the first scenario, when you drop it, it's going to speed up in the downward direction, and then it's not going to accelerate afterwards, continue moving downward with a constant velocity. Just keep in mind, this is the point here where the shingles hit the haystack. So that is the moment right there where we go from accelerating to not accelerating. And then in question 2, which ticker tape did you guys feel was the correct one to describe that? That is correct. It is tape A. And that's because in this top section, that's where we see it speeding up as we read it moving downward. And then here is where we have our constant velocity. And that arrow shows you the time point when it hit the haystack. Okay. Any questions on that? Okay. Then let's look at the homework worksheet. Okay, what is a force? It's any push or pull on an object. Number 2 is choice B. Number 3 is choice C. Number 4 is choice B. Number 5 is choice C. Number 6 is choice D. Number 7 is choice A. Do you want to go over any of those? Yep. So I'm showing you a situation here where the forces on this are balanced, 20 to the right, 20 on the left. Because they're both being exerted inward as pushes, if this were like an aluminum can, what would it do to the can? It would crush it. But since the forces are balanced, we also know it's not going to accelerate, which means the motion will not change. And that's why it's both B and C are both possible options. If they were pulls, if they were both pulling the object, then you could conceivably like flatten it by pulling the outside edges out. So it can change the shape of something depending on where those forces are exerted. But in this case, it might crush it if they're being exerted equally in exact opposite directions like that. Anything else you want to ask? No? Okay. You can use that worksheet to help you with the quiz. It's on your Chromebook today. So go ahead and pull out your Chromebook. You folks can go ahead and work on the 3 questions on your Chromebook dealing with balanced and unbalanced forces. Looks like everybody's done with the quiz. Okay. What we're going to do now is move into our next section of Unit 6, which deals with making some diagrams like you were seeing me show you yesterday, where we're showing the forces that act on an object. And your quiz tomorrow is going to be on how do you draw these diagrams. And I'm just going to give you one to draw. I'm going to give you a scenario in writing, and I'm going to say draw the forces. That's it. Okay. So we're going to talk about how you make these diagrams. They're called free body diagrams, or FBDs for short. FBDs, free body diagrams. What I'm going to ask you to do with this is, of course, define what a force is. And then you need to correctly label and identify all the forces that act on something. And then actually draw the diagrams which show those forces acting using the techniques that we're showing you here for a free body diagram. So to review a force, remember forces are pushes and pulls that objects experience because of how they interact with other things around them. Every force will be symbolized with a capital F, and then we add a subscript after it to tell us what type of force it is. All the forces in the metric system are measured in newtons, not pounds. Pounds is the English system. A newton is the same thing as a kilogram times a meter per second squared, and they're vectors. We're going to draw them lengths to show us how big they are, and a direction to show us which way they're pushing or pulling. Now, on a free body diagram, these are the types of diagrams we draw to help us see the relative size or magnitude and the direction of all the forces that are acting on an object in a particular situation. Now, how many of you have taken POE or are in POE right now? Okay, they do it differently in engineering world than they do in the science world. So it's similar, but not exactly the same. But these kinds of diagrams help us see the size and direction of the forces that act on an object in a particular situation. And basically, it's a special kind of vector diagram. We have drawn vector diagrams before to scale with a ruler and a protractor. And I could ask you to do that here too. Draw the forces with a ruler and a protractor. And what that means is that the length of the arrow you draw would reflect how much push or pull there is, the size of the force. And I could give you a scale, like let's say 1 centimeter is 5 newtons of force. But you know the force is a 20 Newton force. So 1 centimeter is 5 newtons, and you have a 20 Newton force. So that would mean how many centimeters are you going to draw? 4. The arrow would be 4 centimeters long. Okay, you just use a scale to draw it to the proper size. And then you want to make sure that you put the direction on the arrow, because it is an arrow. Without the arrowhead on it, I don't know which way the force is acting. So if I drew a vertical line that was that 4 centimeters for the 20 Newton force, if I didn't put an arrowhead on the top of it pointing up, I wouldn't know whether it was pulling up or down. So you need to make sure you put an arrowhead on it to show the direction of the force. And then every force we draw has to be labeled. You don't just put arrows randomly down. They have to be labeled, and they must include a label for the type of force that they represent. Like, is this a force of gravity? In which case you would put Fg next to it. If it's a normal force, you would label it Fn. If it's the force in a rope, we would label it Ft because it's a tension force. If you happen to know the magnitude of the force in newtons, you can label that too, like I was doing on those shingles. I knew the weight was 50 newtons, so I wrote Fg equals 50 newtons. You can do that as well, but you have to put the Fg. Whether you say it's 50 newtons or not is up to you. Okay. All right. So generally what we do in physics is we will represent every object as a box or a dot. If you do the box method, you have to put the dot in the center of the box. Okay. You could choose it. It's completely arbitrary. Every object becomes a dot. So I like this because I am not an artiste. No way. I can draw a cannon with a cannonball being shot out of it, as you've seen me do. I can draw a dot, which represents everything. A squirrel, a backpack, me, a car. They're all dots. I can draw a dot. So this is right up my alley. Don't spend a lot of time on this. A free body diagram should take you like a minute tops. And then what we do once we get that dot on our page is we draw all the force arrows coming out from the center of the dot or the center of the box with the dot. Now, they're always drawn going out. We never draw them going in. We just don't. Okay, so if it's a push and it's being pushed in, you're actually going to draw that push as a pull on the other side of it. You'll see what I mean by that in a minute. Okay, but all the arrows have to come out of the center of the dot. And if we're doing it to scale, I would measure from the dot to the tip of the arrowhead for its length. Okay, may I go on? All right, and now I wish I could give you a rule about how many arrows you're going to draw on every dot. I can't. I can't tell you there's always 3 arrows on every picture. Or there's always 10. God help us if there's 10 arrows for this course. Okay, there's no rule. The only rule I can give you is that you have to make sure you draw 1 arrow for every force that's actually there. Now, there is a hint that I can give you for purposes of taking a test. You ready for that hint? You know, on our constructed response questions on a test, at the end of the question, I put in brackets a number. Have you realized that? You want to pull out one of like your last test? Look at a constructed response question on the test booklet, not on the answer sheet. Something on the show work. So like question 11 or question 12. Any of those. Do you see how there's a bracket at the end of the question with a number in it? That's telling you how many points the question is worth. On a drawing question, every arrow is 1 point. So if I say draw the free body diagram for this object and it is a 4-point drawing, guess how many arrows you're going to draw? Bingo. All right, so that gives you a little hint in terms of my tests. When I give you a test, that's what you're going to look for to tell you how many arrows you're going to draw. You're not going to draw 5 because it's a 4-point question. You're not going to draw 3 because now you know you're losing 1 point right away. You got to make sure there are just 4 arrows. So the number of points tells you the number of arrows to draw. But you got to know what the force types are in order to help you figure out what arrows you're drawing. So let's just quickly review the force types that exist. The chart I'm going to show you is a duplicate slide from the 6A presentation. You should already have this chart in your notes. Double check that it is there because you'll have it next to you while you're doing these diagrams for a bit. That's the chart. Does this look familiar to you? Okay, so there are 6 forces which act when things are in direct contact, like an applied force, a normal force, a friction force, an air resistance force, tension, and spring forces. We don't write them out in words. We use the abbreviation for every force type. If we're talking about things not touching, it could be gravity, electrical, or magnetic forces. For what we're doing right now, there will not be electrical or magnetic because that deals with electromagnetism, which starts in unit 11 of our class. Okay, So we're not going to deal with those yet. So there's really 10 of them to pick from at this moment. So let's talk about 4 things you're going to do to help you make these diagrams. 4 steps, and then we're going to practice. Step 1, you're going to use your understanding of those forces to help you identify which forces are present in a given situation. So you would have like the chart next to you and say, okay, is there an applied force? You'd be asking yourself, is there someone pushing on this thing? If there's a person pushing or pulling, then you know you have to have an FAPP arrow. If it's on a planet or near a planet, then you got to have an FG arrow. Those are the kinds of things. Is there a spring in this problem? Then you better have an FS arrow. Those are the kinds of things you're going to ask yourself to help you identify which forces are there. Once you've identified what forces are there, you then have to ask yourself, which way are these forces acting? Are they pushing up, down, left, right, or at some angle to the horizontal? Then you're going to make your box or your box with the dot in it, or just the dot. And then draw those arrows going in the proper direction. And once you've drawn each arrow going in the proper direction, you have to label them. Label them with the symbol telling me what type of force that arrow is. All right, now it's time for us to practice. So we're going to go to our packet, page 10. What I want you to do, open up your notes to that chart of the forces so you have it next to you while we practice. Page 10, please. So on pages 10 and 11, these are practice diagrams that we're going to make. I'm going to do all of them with you on page 10. And then I'm going to give you about 5 or 6 minutes to try them on your own on page 11, and then we'll go over those. Want to see if you can kind of figure it out on your own after you see me do them a few times. So in question number 1, it tells us that we have a book which is at rest on a tabletop. And I want you to tell me, diagram the forces that are on the book. Now, the first thing I want you to notice is that it tells us that the book is at rest. That means something about the forces that are acting on the book. We know when something's at rest and it stays that way, that the forces are balanced. That's correct. We need to see balanced forces on this book. So I'm going to make my dot. My dot is the book. That's the book right there. Can't you tell? No, you don't need to. It's a dot. It's the book. Now, what forces are acting on the book? So if I think about like this remote is the book, that's the situation. There it is, just sitting there. There are 2 forces acting on it. Something is pulling it down and something is pushing it up. What's pulling it down? Yes. So we're going to draw a down arrow and we're going to label it FG. That is the symbol for the force of gravity. What's pushing up on the bottom of the remote? The table, right? But what do we call that force of the table's surface pushing up perpendicular to it? Nope, that would be a person pushing it. I'm not pushing it. The normal force, that's right, the normal force. That's an arrow up labeled FN. Now, what do I know about those 2? They have to be balanced, so they are equal in length. Because I'm not using a ruler, I'm going to put little hash marks on them to tell me that they are equal sizes. Does that make sense? You do those little hash marks in math class, don't you, to tell you about sizes? We can do that here too. Okay, let's go to number 2. In number 2, there is a girl who is suspended motionless from a bar hanging from the ceiling by 2 ropes. I want you to diagram the forces on the girl. Okay, since she is motionless, what does that mean about the forces on her? Balanced. That's right. Again, we have more balanced forces in this problem. This dot represents the girl. Now, since the girl is on Earth, what's going to be pulling her down? Gravity. You're going to see this is in most problems. FG pulling her down. What's pulling her up? That's her. The arms are part of her. What outside of her is pulling her up? The ropes. And there are 2 of them. Do you remember what the force in a rope is called? Tension. Okay, here, watch this. There's 2 of them. So I need 2 arrows going up. But do you notice that I am not drawing them as large as the force of gravity? Here's why. These 2 arrows, when I add their lengths together, should equal the length of the FG arrow. That way they would balance. So if the force of gravity was 10 newtons, then each of those tensions would be how much? 5. 5 plus 5 to give me 10. So because they are smaller than this, I have to make each of those arrows smaller. And there are no hash marks I can put, because there's nothing there that's the same size. You with me? Okay, let's go to number 3. We have an egg that is free falling from a nest in a tree. There is no air resistance. Diagram the forces on the egg while it's falling. There's my dot for the egg. Free fall, we know what that term means. How many forces are acting on the egg? 1, and that is gravity going down. That's it. That's what free fall means, only gravity. Number 4, we have a flying squirrel gliding without wing flaps from a tree to the ground at a constant velocity. Consider that there's air resistance. Diagram the forces on the squirrel. Constant velocity means that the forces are balanced. So here's my dot for the squirrel. Something's pulling the squirrel down. Yeah, gravity is going to pull that squirrel down to the ground. What is opposing that? To balance it out. What is it, Eileen? Air resistance. That's F air. Going up to balance it. Number 5, we have a rightward force applied to a book in order to move it across a desk with a rightward acceleration. Consider that there is friction, but there is not air resistance. Diagram the forces on the book. All right, here's what I want you to do. You see how it says there's an acceleration? That means the forces are unbalanced. Okay. And that acceleration is to the right. So I'm going to show that arrow just to help me with this a little bit. I'm going to put my dot for the book below it. And that's where I'm going to draw the forces. I don't put the acceleration arrow on the dot. It's there to help me understand how big these things should be. I'm going to tell you right now, there are 4 arrows to draw. Anybody think they could tell me one of the 4? Aiden, you think you can tell me one of the 4? Going. Yep. Johnny, do you think you can tell me another one? Anson, can you help him? Okay. Which way would friction act? No. No. Caroline, you want to help him out? Give me another force. Okay. Which way is that going to act? Read that paragraph. To the right. A rightward force is applied. That's called an applied force. There's the direction of it. To the right. Look at how I draw that. Large arrow to the right. FAPP. Dominic, you want to give me another force that's acting on this book? Normal force going up. Now, look at this, folks. Notice the length of that is the same as the length of FG. How do I know that those two should be the same length? What? No, well, I want to, what in this question tells me that these two should be the same length? Okay, there's no acceleration up or down. Since there is no acceleration up or down, it means the up and down have to balance. So these have to be the same size. Remember yesterday we had some diagrams with forces in multiple directions? In one direction they balanced, the other they didn't. That's a case here. These need to balance, so they should be the same size. Now there is one more. Miranda, do you know what the other force is? Yes, which way? Correct. Now look at this. Friction always acts opposite the way things are moving parallel to the surface. The surface is horizontal, so the friction's got to be horizontal, can't be up or down. And if this book is accelerating to the right, the friction's got to be to the left. Now, look at the size of that compared to this. How do I know that the friction force is smaller than the applied force? What's the key in this problem, which kind of clues me into that? Jacoby? That's right. And what we learned yesterday is that whichever direction we're accelerating in is where we have more force. We have more force to the right because that's the direction of the acceleration. Okay? Questions so far? Okay, I want you to take 5 or 6 minutes now to work on the diagrams on page 11, please. Okay, you want to check them? Hopefully you did them in pencil. So if you made some mistakes, you can fix them and ask questions. All right, so let's start with number 6. I don't know why I dropped it. There we are. Okay, number 6. Notice it says constant velocity. So that's a clue right there that you should have balanced forces acting on this book. This is what your diagram should look like. There's the book in the center. I'm going to have the weight pulling it down, FG, the table pushing back up, that's FN. Those two have to balance. It says that we are applying a rightward force, so that's FAPP to the right, but there is friction, so that's to the left, FF, and those two forces should be the same size. Notice I have 2 different sets of hash marks, right? Because these are not the same length necessarily as the up and the down. Questions on number 6. Number 7, it says that this backpack is motionless. That means it's at rest. So the forces on the backpack have to be balanced. All right, so hopefully you got the weight acting downwards, FG. The strap acts like a rope pulling it up. So that's FT. The tension and the weight are going to balance. Number 8, constant velocity means that these forces better balance out. So the skydiver would have its weight pulling him down and then air resistance acting up to balance that. So far, so good? All right, number 9. It says we have a rightward acceleration, which means in this situation, the forces will not balance. So the forces on the sled, we're going to have the weight pulling down, the ground pushing up. That's called the normal force. We are applying a force to the right, force applied to the right. There's my FAPP. And then there is friction between the sled and the ground, the snow. That force of friction is to the left. Since the acceleration's to the right, I know the applied force should be larger than the force of friction.
You have to put the A with the arrow like to the direction above it.
No, not necessary. I didn't put it here, but if it helps you to figure out which one's bigger, do it. Okay. Number 10, this football is rising upward to the peak. I think most of us know that as things go up in the air, eventually they're going to stop, which means this football is going to slow down on the way up. Since it's slowing down, that means the forces on it are unbalanced. Now, there's 2 possible diagrams for this. We don't know if there's air resistance or not. So if there's air resistance, it would act opposite the way it's moving. It's moving up, so air resistance and the weight would both be down. Or if there's no air resistance to consider because it's really not moving that fast, you would just have the weight acting down on the football. That's it. If you drew an applied force, that's only going to be there when the football player is in contact with the ball. This has already been booted. You see that? It's after it was booted. You're not touching it anymore. So there's no applied force. The last one is about this car coasting to the right and slowing down. Since it's slowing down, it is an unbalanced force situation. There are 3 forces only. And those 3 forces, by the way, what does it mean when we say something is coasting? A car. If your car is coasting, is your foot on the gas or the brake? No, it's off. That's why your car slows down. Okay, you're not giving it any more gas to keep going forward. So this is it. The normal, the weight, and the friction force. The normal and the weight have to balance because the car is not accelerating up or down. There is no applied force because there is no person outside the car pushing the car forward. That would only happen if the car wasn't running and you needed the car to move forward. You'd put it in neutral and then push it. But there is no person outside of the car making it move. So there's no FAPP. That's it. All right. Any questions on this? if you wanted to, on this one, the car is moving forward, so its velocity is to the right, but because it's slowing down, the acceleration is to the left. That's why we only have a net force here to the left to produce that leftward acceleration. Okay. That's not necessary to draw them, but that's why. It kind of now explains why it slows down, because we have an unbalanced force acting to the left, opposite the velocity. Okay, questions on this? All right, let's talk about what your written assignment is for tomorrow. It's pages 13 to 17 here. Let me explain what's what, first of all. Turn to page 12. Page 12 is here. Oh, I guess I'll describe it right after the break, okay? Take your break, and when we come back, I'll describe what's going on with the homework. Just put the door stop down on the door so it stays open for you. Yes. Yeah, it's only gonna take like 5 or 10 minutes, so. Good. Yeah, I needed it to recover from Monday while I wasn't here. So I was out of town on Monday and I didn't get home till 10 o'clock at night. So I needed it.
My neighborhood had like a snowball fight. We had a bunch of little kids running around, so that's-
No, I stayed on the couch watching Netflix with the fireplace on and all 3 dogs on top of me for the day. And I sent my daughter outside to shovel because I can't lift like that. I'm still not allowed to lift and without hurting myself. Last thing I want to do is hurt myself. I got enough going on. All right, so let's talk about what's going on here with the homework. So, here on page 12, page 12 is meant to just kind of reiterate what was in the chart that we took notes on in section A, the types of forces. But there's some problems with it. The symbols that they use on page 12 are incorrect. So I'd like you to correct them with me now, so you always use the proper symbols. Depending on what course you're in or where the course is being taught, they may use different symbols. New York State, these are not the symbols we use. So weight is never the letter W, and we don't write the force of gravity as F grav. They're both symbolized as FG. FG can be either. Normal force will only be Fn. Spring force will only be Fs. Sliding friction forces will only be Ff. Air resistance will only be F air. Tension is neither of those. It is Ft. And the applied force is FAPP. Okay, so you can use this page kind of as a summary guide to help you if you're having a difficult time deciding what forces exist. You can look back at page 12. All right. Let's now talk about the written piece, pages 13 to 17. I'm modifying the assignment from what's on these worksheets. On page 13, 14, 15, and 16, it's the same thing. They're going to give you a description of what's happening. This column is asking you which of these forces are there and which ones aren't. You circle P or A, present or absent. Cross out the explanation column. You're not going to explain to me why they're there or not. That to me seems redundant. Cross that out on all 4 of those pages. So you see, this assignment just got a lot easier, right? Because you just got to say, oh, yes, this is there. No, it's not. Blah, 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 blah. Okay. Page 17 is where I'm now asking you to draw the free body diagrams for each of these situations. This page should be done in pencil because if you make a mistake, you're not going to be able to fix it. It's their drawings. Okay, so page 17 should be in pencil. You're not going to use these symbols. Use the symbols that we use in our course. Okay. Any questions? Okay, that is the written assignment for tomorrow. It should not take you that long if you understand forces. Let's put this to the side, and we're now going to move into our next topic, which is friction. You need out your reference table for this as well, please. And what we're going to learn about today and tomorrow and on a lab on Monday are different types of frictional forces. What I'm going to ask you to do is define the term force. I'll ask you to determine weight and normal forces. I'll ask you to explain what is meant by friction. Then I'll ask you to distinguish between static and kinetic friction forces. There's 2 kinds that we work with in this course, static and kinetic. What do they each mean? What type exists when? Explain to me then what 2 factors affect how much friction you might have, and then solve some problems. So there's a lot of conceptual understanding that goes with this, and we're going to take some time to discuss it. All right, so let's do some review. In order to understand friction, we do have to understand what weight is. And this was part of your video notes on Monday that I asked you to take. We calculate weight using that equation, G equals Fg divided by M. Let's just double check that you checked everything off here on your reference table, page 6. Did you check off that equation as you took notes? G is Fg divided by M on page 6, which means in the right-hand column, you should have checked off already. Lowercase g is the acceleration due to gravity or the gravitational field strength. That means you're either going to measure it in a meter per second squared or as a Newton per kilogram, depending on which of those terms you're referring to. This Fg, let's check that off. That is the weight of the object or the force due to gravity measured in newtons. And m is the mass in kilograms. Which means that the way this equation is written, it's helping you find the gravitational field strength at a particular location on the Earth. If I wanted to know your weight at a particular location, I would have to manipulate this, multiplying both sides by m, so the weight, Fg, would be the same as m times g or g times m. And that's what you took your quiz on yesterday. Okay, so let's now talk about the normal force. The normal force is Fn. This is the support force from a surface on an object. And it's always perpendicular to the surface. That's review from section A, that the normal force is a perpendicular force of support from a surface. And then friction force is Ff. This is the force exerted by a surface as an object moves or tries to slide across the surface. It will always try to oppose any motion that might be there. It's an electromagnetic interaction. That's the category of force that it's in, which means it's in the second strongest category of force we have, the strongest being the strong nuclear force. This type of force only exists when surfaces are in contact, and it will always be parallel to the contacting surface. That's all review. That was all from your notes back in section A. Let's now get to the new stuff. Where is friction coming from? As I mentioned to you in that previous slide, this is an electromagnetic interaction that comes from surfaces being pressed together. I don't care what type of surfaces you have. My desk feels really smooth, but if I put my desk under a microscope, this is what it's going to look like. Really rough and jagged. Another surface it's in contact with will also be rough and jagged. And when these two surfaces try to slide across each other, these jagged points, microscopic contact points, get in touch with each other, and the protons and electrons in those two materials start attracting. Right? Protons and electrons attract, which means that we get an attractive electromagnetic interaction between these two surfaces, and that is friction. So it's caused by intermolecular attractive forces that are exerted between the molecules in those different surfaces. Now, if surfaces are not being pressed together, you're not going to have any friction. I mean, let's think about this for a minute. I got my two hands here. They're like this. If I try to slide one hand across the other, they're not touching each other. Is there any friction between my two hands right now? As soon as I press them together and I go back and forth, isn't there friction there? Absolutely there is. Okay, that's what's going to heat up your hands eventually by doing that a number of times. Now, try this with me. Take your two hands, just lightly press them together and rub. A lot of friction or no? Not much. Okay, now really press them together and try to rub them. A lot harder to do that now, right? That's because there's a lot more friction there. The more you press surfaces together, the more friction you're going to get. So let's talk about the different types of friction that exist. The first type of friction you need to know about is called a static frictional force. And this is the type of friction that exists before surfaces actually start slipping across each other. It's there before surfaces slip and slide. Now, what's interesting about static friction is that the amount of static friction you might have can change. It's variable. It's not one fixed number. Let me try to describe for you what I mean by that with an example. Can you all see that I have a small file cabinet here? Okay, I got a lot of junk in this cabinet, like my fan, right? My little purple fan that I pull out when I start getting a hot flash. There's a lot of stuff in here. I'm going to try to push it right now and make it move. Okay, I am pushing on it. Is it moving? Okay. Let's do some numbers on this. Let's say I'm pushing it with 1 Newton of force towards Dominic. My applied force is 1 Newton that way. It's not moving. So how much is the force of static friction acting back on me? 1 Newton. It's balanced because it's not moving. Now I'm going to push it a little harder. Now I'm pushing with, let's say, 5 Newtons of force. Is it moving? This is still static friction, which is preventing it from moving. But how much is the static frictional force now? You see, it just went up. It changed. Okay, now I'm going to push it with 10 Newtons of force. Oh, and then it slipped. That 10 Newtons meant up to that point, how much was the static friction before it slipped? So how much was it? 10 Newtons. It was balanced. Before it slipped, it was 10 Newtons. And then all of a sudden it slipped. What we just observed is that variable amount of static friction that's there. It can change up to a point when then it slips. So static friction is going to increase up to the point to prevent relative motion. And that limit where the motion occurs is called the threshold of motion. And we'll make a graph for that in just a minute. This is a pictorial representation of what I was trying to illustrate with my filing cabinet. In the top picture, can you see that there is a small force in the rope of me pulling a tension, small tension? There's a small static friction force in the opposite direction. These have to balance because it's not accelerating. In the next diagram, notice my pull has increased. You see that arrow's bigger now? Notice the static friction force is going to increase to match it because, again, it's not accelerating. We have to have balanced forces. Then I increase it even more. Notice the friction force increased up to the point when, boom, it slips. This is what we call the maximum static friction force at that moment when it will just slip. Okay, it increases up to that point. And once you go beyond that point, now you'll get it to move. Once it begins to move, it changes to a different type of friction known as kinetic friction. Kinetic friction is opposing actual slippage of the two surfaces. The two surfaces now begin to just slide across each other. Now, unlike static friction, the amount of kinetic friction you might see is always going to be one value. It's going to be a constant value for the situation. It's not going to change based upon what you're doing. So long as the surfaces slide across each other, that kinetic frictional force will be the same number. Doesn't matter how they're moving. And it turns out that once you get something to move, the amount of kinetic friction that's there is always less than that maximum static friction amount. That's why I had to give it a real oomph to get that file cabinet to move, and then I could back off. Have you ever noticed that? To get something to move that's really heavy, you got to give it a good shove, and then once it's moving, it's like you broke that real strong attraction between the two surfaces, and then it will slip a lot more easily. So the kinetic friction force is always smaller than the maximum static frictional force that will exist between the same two surfaces. Now we're going to illustrate this on a graph. And I want to jump to my document camera so we can all draw this in our notes together. And then we'll talk about an application of this. Okay, so let's make this graph together. This is a graph of the frictional force, which is FF, versus the force that we apply to an object. Now, what we just said in our notes is that the frictional force will balance the applied force up to a point. So as I increase my applied force, the amount of frictional force will increase up to a point. And this point here is our maximum static friction force. Static friction is FFS. S for static. The word max is after it. That's the largest static frictional force we'll have. This is a value of 0. That's a value of 0. And between these points, this is where the static frictional force will balance the applied force. There is no motion, no slippage of the surfaces in that range. Once we get to this point where we reach our maximum static friction force, the friction force decreases and then becomes a constant value. And this value occurs when we now have kinetic friction, FFK for kinetic friction. Now, what we can see from this, like if I were to come back over here, you would read a smaller value for the kinetic friction than you would for the maximum static friction force. What this means, and we can write this as an equality, is that our maximum static friction force is always greater than the amount of kinetic friction that's there for the same two surfaces in contact. And the amount of static friction that we can read off the graph will be somewhere between 0 and the maximum value. This amount is determined by balancing your free body diagram. That's what you have to look for, is a balanced free body diagram. Okay, that is what we were just discussing with my file cabinet situation. This point here, by the way, as I said, when it breaks free and slips, that point is called our threshold of motion. So there is no motion happening in this segment of the graph. Nothing is sliding. It's all stuck. Once it slips, now we're here. Okay. All right. I want to talk to you about this scenario. I've got 2 tires here on a car. And the misnomer is that when you're driving your car, because the car is moving, that it's got to be kinetic friction. And that's a bunch of BS. Let me talk to you about why. Why do we have rubber on our tires versus wood tires on our car? More grip. We need the tires to grip the road surface. Look at this picture over here. This is when you're driving your car and you have control of your vehicle. Your axle on the car spins like this, which causes the tire to spin in this direction. This point of contact with the road surface is where the tire sticks and grips. It doesn't slide across it. It sticks and grips. And that stick enables it when the axle turns to make your whole wheel move forward along with the car. So this type of friction that's present when you are driving your car and you have control of your vehicle is static friction. I want you to think about this. I can illustrate that even with walking and my feet. Can you kind of see my feet? No, you can't. Maybe better here. You kind of see my feet? Illustrate. Let me illustrate. If my feet, my shoes didn't stick to the floor to enable me to walk, that's what would happen. This is sliding. What type of friction is sliding? Kinetic. Kinetic is when things slip. Now, to walk, is my foot going to slide off the floor? It sticks. That's the same thing that happens with your car. The tire, that point sticks. So when it sticks, it's static friction. There's no slip. Now, if you went out on Tuesday to drive, which if you're learning to drive, you do want to practice when the roads are crap, but don't practice it on the road. Say, hey, mom or dad, can we go practice driving in winter weather at the mall? Go to a big empty parking lot, okay, with lots of snow. And what you want to do is go relatively fast in a circle so you lose grip with the road. You're going to go into a skid. It's going to freak you out. This is why you want to practice what happens, because eventually at some point in your life, it's going to happen. And you don't want to be freaked out on the highway. Practice it first where there's nobody around you so you can't get into an accident. So you know what to do when it happens. Once you know what to do and you've practiced it a few times, when it happens, you'll be real safe. You won't get into an accident. So here's what you do. This is a skid. When the tire doesn't grip the road, you'll feel it when it happens. Your car, in whatever direction you are moving, will now go straight. So I'll give you Wednesday, yesterday morning on my way here, they did not plow the intersection with my road and the main road. So when I went to turn onto the main road, my car went into a skid. I was not going very fast, fortunately. So what you do when you go in the skid, let's say my car's going in this direction, but I wanted to go this way. This is counterintuitive. My car's going this way. I'm trying to go that way. You take the steering wheel and you go this way with your steering wheel. Go in the direction of your skid. That will turn your wheels in the direction you are moving. And as you do that, take your foot off the gas and the brake. No brake, no gas. Let your car coast for a split second. It allows your wheels to slow down a little bit. And if they're pointing in the direction of motion, you will then reestablish that grip. You'll feel it. You'll feel that, oh, it's not sliding anymore. And then you can take your hands and put it right back in the direction you want to go. It happens very fast. But if you don't practice it, it is the most uneasy feeling in the world. And you don't want that to happen to you when you're actually in traffic, because that's how you get into an accident. And as a young driver, you do not want to get into an accident, because then your insurance rates for a long time are going to be through the roof. Okay. And if you just got your license, you get into an accident. Sorry. Now you've lost your license for 6 months, I think is what New York State will do. They're going to take it away. So you have to be careful, but you got to practice it. So next time we have a snowstorm, I know your parents are going to hate me for saying this, but then they're going to realize I'm right. You need to practice driving in these types of conditions, because we live in New York. It's like we get snow every season, every winter. So you want to make sure you do practice it, okay, just to be safe. But it's the difference between static friction, which is your friend when you're driving, versus kinetic friction, which will cause an accident. So please be careful of that. All right, so let's talk about how we find the frictional force. If the forces on you are balanced, that means you are not accelerating. That's either because the object is at rest or moving with a constant velocity. It's really easy. Just balance out the forces on your free body diagram, because you're in equilibrium. That's what we did yesterday. Balance them out. That means the applied force is the same value as the frictional force. Doesn't matter what type of friction it is. If you have no acceleration, either because you're at rest or you're moving with a constant velocity, the frictional force has to balance the applied force. It's just in the opposite direction. Isn't that what balanced forces means? That's real easy. See, so you already know how to find frictional forces if it's a balanced force situation. Thing is, we don't always know if it's a balanced force situation or not. in which case we're then going to want to calculate it with a new equation on our reference table. So let me go over that with you. All right, can I go on? Yes? We already did that. All right. Now, if you have to calculate it, remember that there are two things which will determine how much friction there is. The first is what the materials are that are in contact with each other. This is why winter driving conditions, the town goes around and in addition to plowing the road, they put stuff on the road surface. Salt and sand. They put both, salt and sand. Salt is there because it lowers the freezing point. It's one of the colligative properties. When you add salt to things, it lowers freezing point depression. So that way you won't have ice on the road. What's the purpose of the sand? More grip, more friction, right? Think about this file cabinet. I have it here on this nice shiny floor, which is really gross because they haven't waxed them since the summer. Okay. If I take this file cabinet and I now transport it to the beach on the sand, is it going to be easier or harder to push this on the sand than it is here on the floor? Harder. Why? Because there's more friction with sand. Okay. Why do we want more grip on a road surface when the weather is bad? That way you have control of your vehicle. So it does depend what materials are in contact. And then it also depends on how much you press them together. And we already did that demonstration with our hands. The amount they get pressed together is what we often call the normal force. This is why, let's say you have you have a sports car, very light. They're going to tell you in the wintertime to put bags of sand in your trunk and in the back seat of your car. Why would you do that? That increases the mass of your vehicle, which increases the weight, which will therefore increase the normal force, the amount your car is pressing into the road, which would therefore change the frictional force, increase it. Remember, pushing hard versus just light. When you push hard together, there's more friction. Now, this is all illustrated in an equation we have, and this is the equation that we use to illustrate this. The equation for frictional force is FF is mu Fn. This is the Greek letter mu. Mu. Not meow or moo. We're not cats or cows in this class. Mu. It's also the same symbol that you've seen for micro before, but it's not a metric prefix in this case. In that equation, the FF stands for the frictional force measured in newtons. Mu represents this thing called the coefficient of friction. It's a unitless value which changes based upon the materials that are in contact. It's material dependent. And Fn is the amount of pressing, the normal force in newtons. Now, this is on our reference table. So let's jump to our reference table and check off some stuff here. There's a lot of stuff to check off with this. Be careful. You don't want the mu to look like a lowercase m. It's a U with a tail in the front. Lowercase u with a tail in the front. Okay, let's go to our reference table. Page 6. Here's the equation I want you to check off. FF equals mu Fn. Now, in the right-hand column, start with FF. There is your frictional force. That must be measured in newtons. Now check off Fn. the normal force measured in newtons. Now head down to the bottom. There's the mu, the coefficient of friction. This is a unitless value. This is one of only 2 times this year that when you write a measurement, you're not going to put a unit after it. There's only one other time this year. Otherwise, every time you write down a measurement, it better have a unit after it. This one will not. Now, as I said, this is determined by the materials in contact. We give you a small sampling of materials in contact that we use often in Regents Physics here on page 1 of your reference table. Please check off this chart. These are the mu values, the coefficients of friction for a sampling of materials that we often ask about on the Regents exam. So we'll be using these in class a lot. There's a lot of them. If you go online, there's something called the Handbook of Chemistry and Physics. We used to have a paper volume of it in our reference section at the library. The book was about this thick, weighed probably about 15 pounds, probably 3,000 pages. Maybe 5 pages, tiny, tiny print of coefficients of friction for different materials. We just know what they are. Scientists and engineers look them up. But you'll see that I give you not only coefficients of kinetic friction, but static friction for different materials. Notice that if I'm dealing with the same material, the static coefficient of friction is larger than the corresponding kinetic one. That is always the case. That's always the case. That's always the case. You see that? Every single time the static value is bigger than the kinetic one, which indicates that the maximum static friction force will always be bigger than the kinetic one. Okay, let's now go to page 18 in your packet, and let's try practicing with this. Keep out that reference table because you're going to have to look things up. The first question on page 18 dealing with friction just wants us to be able to identify the coefficients of static and kinetic friction. Notice I write mu s and mu k. This is the static one, that's the kinetic one. We're going to go around the room. Let's do the static column first. Aiden, can you please identify rubber on dry concrete, the static value?
0.
The static value?
0.90.
There we go. Gianni, what is it for rubber on dry asphalt?
0.85.
Good. Anson, how about waxed ski on snow?
0.14.
Correct. Caroline, how about wood on wood? Mm-hmm. Dominic, steel on steel?
0.74.
And Miranda, how about copper on steel? Good. All right, now let's do the kinetic coefficients of friction. Eileen, how about rubber on dry concrete? Good. How about rubber on dry asphalt? Kine? No. That's the static one. There you go. How about wax ski on snow, Huzaifa? Yeah. Anya, how about wood on wood?
0.30.
Good. Morgan, how about steel on steel?
0.56.
Good. And Manor, how about copper on steel? Good. All right. So let's now go to part B. What do you notice about the coefficients of static friction compared to the coefficients of kinetic friction for the same surface combinations? So every static coefficient compared to its corresponding kinetic one. Angela, what do you notice about all of them? That's right. The mu s is always greater than the mu k. It's always bigger. Mu S is always larger than the mu K. So Liam, what does that mean about the, I need to insert a word here. The maximum static friction force compared to the kinetic friction force. If the static coefficient of friction is greater than the kinetic one, what does that mean about the maximum static friction force compared to the force of kinetic friction? That's right. It means that FFS max is greater than FFK. Because FF is mu FN. So if you have a bigger mu to plug in, you're going to end up with a bigger FF. Mu and FF are directly related. Okay, part C. Which of those materials requires the greatest force to start it moving? Which of these requires the biggest force to get it to start to move? Ashley, what do you think? That's right. Now, how did you know that? That's right. So this has the largest mu S value. And if you wanted to get it to start to move, you have to overcome static friction to make that happen. So this has the largest mu S value. Okay, let's now go to page 19. We have a smooth wood block being placed on a smooth wood tabletop. You find that you must exert a force of 14.0 newtons to keep the 40.0 newton block moving with a constant velocity. First thing I want to do is draw a free body diagram of this. Alexis, why is this phrase constant velocity important? That's correct. Good. We have balanced forces here. All right, so let's start. That dot is my block. Alucci, can you name a force acting on the block? Going? Correct. Jacoby, can you name another force acting on the block? Going? Yep. Aiden, can you name another force acting on the block? You find that you must exert a force of 14 newtons to keep it moving. Going? It doesn't say, so you pick. Okay. It's not balanced yet, so there's got to be something else there to balance this out. Gianni, what's going to balance it out? Yeah, which way? Yeah. Now, since they're balanced, tell me what forces balance here. Anson, can you tell me what's balancing? There's two pairs of forces that balance. What's one pair? Okay. And Caroline, what's the other pair? That's right. Now, we have some force values being given to you in the question. I want us to label those on this picture. Dominic, what is this 14.0 newtons referring to? Which of those forces? You must exert a force of 14.0 newtons. So which force is that? That is F applied. That's right. So since F applied is balancing FF, Miranda, how much is FF? 14.0 newtons. Now, what force, Eileen, is the 40.0 newtons referring to? Any idea? I'm going to try to help you out. This is an adjective describing the block, right? It's a 40.0 newton block. if this was not a metric system question, it would have said that you had a 40.0 pound block. What would that have been? The weight. It's the weight. FG. So Kine, what does that mean, the normal forces? That is correct. Now, by putting those Newton values on this picture, you have your givens already for part B. You don't have to relist them. Part B says, what is the coefficient of kinetic friction? That means I am asking you to find the mu K. Now, we're going to calculate instead of what is, calculate. We only have one equation that involves mu. Because I thought, what is that equation that involves mu? That's right. And what we'll do tomorrow is we'll move it around and solve it for mu after we go over the homework and take our quiz. Okay? Those of you that owe me labs, including Aiden, Gianna, Angela, and Manure, I am after school today for you to finish up those labs and get them turned in, but let's do that soon. If you are not able to stay today, let's try to make that happen next week. Morgan, you have a quiz to take online from last period. Okay. No, you can take